Uh-oh, Amanda's got food.
I did. I was so hungry that I bought Skittles from the vending machine.
Oh my gosh, these are the new Skittles. They have the new green apple. Those are my absolute favorite. But these Skittles, they claim that they have an even distribution of colors, but I think they're always stingy on the green apple, which sucks because that's my absolute favorite one.
Well, you know, Carly, we could do a 2-sample Z-test, right?
Yeah, exactly.
But guys, I like the orange ones.
Oh, and come to think of it, I really like the red ones, so we can't do a Z-test anymore. What are we going to do?
Because this is statistics and we have to think about our food, we're going to do the chi-squared goodness of fit test.
And that brings us to Chapter 22, Part 1. So, we just randomly got a package of Skittles out of the vending machine and decided to count how many of each color we got. And there are the results right there. This is what we observed. The hard evidence right there. That's our package. And so we were able to fill in the first column in our chi-square table. So this is what we observed, but what would we expect? That's our expected column.
So we counted them up, and we can see we have a total of 60 Skittles. There's a total of 60 Skittles in each bag, and they're claiming that there's an equal amount of each color in each one. So therefore, we take our 5 categories and divide that into 60. So 60 divided by 5 gives us 12. We're expecting 12 of every color.
Oh, okay, so all of our expecteds are the same, since they claim there's
Correct.
an even
So the same is
distribution.
equal. All of our expecteds will be the same.
Say, Carly, you might have been on something
Oh
here.
my gosh, look at this. The green. I told you the green has the lowest amount. 9. We expected 12, we only saw 9.
But look at orange. Orange got gypped too. Only 10.
You're right.
But I got lucky with my red.
Yeah.
So I guess that means we have to look at all of our categories. So our next step here, we're going to compare this. We're going to do our observed minus our expected. So we want to find the difference here.
Okay, so we have 15 minus 12 for the first one, 3. And then 10 minus 12, so we observed a smaller number than we expected, so that's going to be a negative number, negative 2. And then continuing on, we get 3, negative 3, negative 1. And then when we add all of these up, what do we get?
Is it 0, Carly?
Yeah,
Is that-
so
Does it always equal 0?
it does always equal 0. These are kind of like the deviations that we talked about before. They're always gonna, the sum of the observed minus expected is always gonna be 0.
Oh, so that's why it wouldn't be a good measure of, like, because you'd think you want to see if that number is really big, if the differences are really big, then you would say, hey, they're being unfair. But since it's always going to be 0, the average is always going to be 0, I guess you got to do something else.
Yeah, so what do we usually do when we have that problem?
I think I remember something about a square.
Yes, that's exactly right. So now we're gonna square all of these.
Oh,
We're
to get
gonna
rid of the
take-
signs.
Yes. That way we can get rid of these negatives. We don't want any negatives. So we are going to take 3 squared, which is 9. Negative 2 squared.
That's 4.
Good. And then we just keep going down to get 9, 9, and 1. So now we can add these all up, right? They're all positive numbers, not going to equal 0.
You could add them all up if if the expecteds are all the same, and I think they are.
They are, yes.
So we could add them all up, but what if the expecteds weren't? Maybe we should do the general case.
Yeah, maybe we should let's just keep going in our chart. So the last step is to take this column, the observed minus the expected squared, and divide by each individual expected value. So sometimes this column's not going to be exactly the same for all the different categories. Here it is, but in the general case it's not going to be. So we're going to take 9 divided by, we expected 12. And then here, 4 divided by, we also expected 12. So basically all these numbers divided by 12.
I'll go get the calculator.
Oh, I see, because this time you have a common denominator. So you
Yes.
could have added them all up and divided by 12.
We could have just added all of these up and divided that by 12
But
since
sometimes you
these are all the
don't have
same.
a
But that's
I got
not
it.
always the case. So we wanted to go ahead and actually calculate that last column. And now we need our chi-square statistic.
Do I add them all up?
Yes.
This calculator's not very fancy.
Got my TI-84 plus.
You can just add the numerators.
Yeah.
9 times 3 is 27 plus 5 is
32
divided by 12.
2.67. All right, perfect. So we have our chi-square statistic. Now we need a p-value.
So we didn't state this explicitly, but let's talk about the null hypothesis of the data. If you remember, the null hypothesis is that everything is normal. There's really nothing else going on. So in this case, the observed data, so what we did when we counted the Skittles, fits the model good. Remember, good fits with goodness of fit tests. So what does that mean? It means it fits this box well. So we have 5 different tickets with the red ticket, the orange ticket, the yellow ticket, green ticket, the purple ticket. So here the null hypothesis assumes that there are millions of tickets and that it is equally likely to draw any of these tickets. So that means if I draw from this box 60 times, I will get 12 of each tickets. Now, on the other hand, the alternative hypothesis states that the data does not fit the model good. So what that means is that, like Carly said, and like Jill says, there's something weird going on, that when we draw from this box, it's not going to be even, and it's not going to be even just due to chance, but rather something else.
So the next step in the process, which we already did over there, but to write it out for you, is to find our chi-square statistic. We don't think, Carly says, okay, she's getting gypped on greens, I'm getting gypped on orange, but we gotta look at it a broad point of view. We gotta find out this number. So we found our chi-square statistic over there with that table.
And now, after we have our chi-square statistic, we need a p-value. And for a p-value, we can't look at a normal table, we can't look at a t-table, but now we're doing a chi-square goodness of fit test, we need a chi-square distribution. And the chi-square distribution is actually pretty similar to the t-distribution in that it varies depending on the degrees of freedom. So that brings us to our next point. We need to find the degrees of freedom first, and then we're going to use the chi-square statistic and those degrees of freedom to calculate our p-value.
We have to figure out our degrees of freedom. Now, how many categories, or what is our degrees of freedom? How many categories are we looking at?
60?
No, not necessarily. That's how many Skittles are. That's how many Skittles we're getting in a bag. We want to know our categories. So our categories here are red, orange, yellow, green, and purple. So that's 5.
Okay.
We have 5 categories we're looking at.
Okay.
So we take that 5 for a number of categories, and we subtract 1. So our degrees of freedom equals 4. So the next step is you take this degrees of freedom, and you go to our fabulous chart. All right, so we're on a
looks
chart.
like the T one, doesn't it? There's lots of, you have to look at all that.
They look really similar, and they are similar, but a chi-square test is just a little bit different. So we're going down here to our degrees of freedom, which we found, 4, and we go all the way over to our chi-square statistic. Our statistic is 2.67. So 2.67 falls in between 70% and 50%, so 2.2 and 3.36. So our p-value is somewhere between 50% and 70%. That is an enormous, enormous p-value. In conclusion, we have to figure out, do we accept the null dull? Are they doing what they're saying? Or do we say there's something else going on?
What was the p-value again? Should we write that?
Our
I forget
p-value?
what it was now.
Over here, it's somewhere between 70 and 50. That is an enormous p-value.
Oh my
Remember,
goodness.
It's massive.
p has to be less than 5 to be considered statistically significant. So,
Wow.
based on this bag, Skittles can say they're doing exactly what they claim.
We cannot reject the null.
We cannot reject the null.
And 1 iota. It seems like we, in this case, it's almost like we have to accept they're telling the truth.
They're making claims and standing by them. Taste the rainbow, think about the rainbow.